Good morning, everyone. So today is the second day of the year of the ox. So first, I will say Happy Chinese New Year. And today we are going to discuss AMC 10B and 12B. And the first thing I think we start with will be some statistics. So there are a few hundred students in Hong Kong and Macau participating in AMC 10B and 12B. So first, let's see the score distribution. So here is the score distribution for AMC 10B. And you could see, for those of you who have already attended the AMC 10A and watched the live session, and you will notice that probably for this curve, you could see that it is a little bit shifted to the left. And all the scores, all the measures, they are slightly lower than AMC 10A. So the next page would be for AMC 12B. And a similar situation. So the average score is a little bit lower. And although because I think we have a relatively small data set, the top 1 percentile actually increased. Next would be the thing that we need to guess, and many of you are quite curious about it, would be what would be the cutoff scores for this year. I think there are two levels of uncertainty here. The first level of uncertainty is what? Is how many percentage of students will be invited to AME. That is something that is not set in the AMC rule. As you can see that in the past, normally, so top 2.5% of students in AMC 10 will be invited to AME. So hearing that here the word is top 1% and top 5%, then these cutoff scores will be between the two scores for most of the time. But in recent years, in 2020, you'll notice that these two numbers are actually smaller than the top 5% score, which means there are more than 5% of students are invited to AME. So here the uncertainty here would be whether here we do have 2.5% or more. Right? So that is uncertainty here, and here the same, right? So normally it would be 5% will be invited to AME, but it could be more, right? So that is one uncertainty, and for that part, I think there's no way we can guess. And a more reasonable guess that we could do would be how to identify these four numbers. And so now, given that we have the chat room, and maybe you can guess what would be the top 1% for these four exams. If you have some idea, maybe you first type 10A or 12B, and then you guess. So top 1%. And let us see what people really think. All right, so if you have some idea, you can try to type it in the chat channel, so we could have a guess, and that also is some statistics that we can do. Anyone? Okay, so someone guess it's 10A is 127, and 10B is 120. Any other guess? So for me, I think there's a few factors that we need to consider. The first factor would be Of course, this is an online competition for most of the participants, and that could have two-way effects on the performance. And the second thing is the total number of participants, whether it's still the same scale as last year or it's a little bit smaller, right? And the third thing would be if we really can calculate these cutoff scores globally, then probably the score will change depending on how many percentage of students are from mainland China, right? So that would be a few factors which we really don't know. Based on the statistics of Hong Kong and Macau, so here is my guess about the AMC 10 and 12 cutoff scores for the two awards, which is top 1% and top 5%. So probably we'll guess these two numbers will be just about the same. So 10A is slightly easier. So for 10A, I think the top 1% will be 129. And here it's probably 111. And for 10B, the top 5% is 102. And that might be 1, 2, 3. And so this is not really my guess. This is more or less the performance of our students here in Hong Kong and Macau. And we'll check later to see whether this is really the next estimation of the overall average. All right, and then we move on to the next page. And this page lists the 10A and 12A problem difficulty level. But at least you'll see why I see 10B and 12B are harder. So for 10A, at least you'll see there's something. Even the hardest problem is about 10%. Here, even 12A, that's about like 4%. But if you look at the statistic for 10B, the most difficult question, which is the first question we are going to discuss, the correction ratio is below 1%. And you see also there is even the problem 7 is a difficult problem. Do you still remember what is problem 7? And so that question is about 4 circles. It's not really easy to design the maximum one. And this question is about 2 square root of 3, whether it's greater than 3 or less than 3. All right. So you'll see that's 10B. And then 12B. 12B is very similar, and all the questions here are very difficult. Not only the last 5, it's even spanned to the last 10 questions. Okay, so now here are some statistics, and then what's the plan for us for the real math? The real math is based on the correction rates. So I'm going to explain the 10 most difficult problems, which means the 10 problems with the lowest correction rates. And so to make the class more efficient, so what I'm going to do is for some of the problems I already copy down my scratch paper to the board so that you could see how I solve it, and also I will explain why I think this way. All right, so of course the first question to start would be the problem 25. And actually, this problem 25 is shared by both AMC 10B and AMC 12B. And for this question, a very important part would be we find out what is a starting point to do this question. And for now, can you type what you think? Can you tell me why it's difficult? Or what is the idea you have? If you have anything, can you type it on the chat channel? So in this question, we have a lattice point, a set of lattice points, and the coordinates are between 1 and 30. So which means x is between 1 to 30, y is between 1 to 30. Then how many points are there? that's clear. We have 30 times 30, we have 900 points, right? So that is something for sure when we read the question. And then what's the next condition? The next condition is we want to consider a line. And this line will kind of cut these 900 points into two parts. On the line and below, they have 300. Then what does it mean? The rest part would have 600 points. So this would be a line. And then you have a guess. What would be this? What would be the easiest line that you can think of, like in this form, y equals mx? So the easiest form, of course, would be y equals x, right? Because y equals x is kind of like with just a 45 degree, that is the angle bisector of the x-axis and the y-axis. And then for that line, how many points would be on the line as well as below? This would be like slightly greater than 450, right? So then we know for whatever the m that contains 300 points on the line and below the line, so m must be slightly, maybe much slightly less than 1, right? So that would be all the things that you can feel after you read the question. But still, you don't have any clue what's next. And for this question, I also probably pause for a minute or two or maybe 3 minutes to think about where to start with. And they say all the possible value of m lie in the interval, and this interval must be very small, but they want you to calculate the sum of the denominator and numerator. So the 5 choices give you no clue at all. And so you may need to find a starting point. Then there are many things that I actually think of. Another way is one part that you can think of. Okay, how about you try to express it in another way? Actually, you could. And what that other way? This other way just means m, and then you take its floor function, which means the greatest score less than or equal to m, and then so that means corresponding to x equals 1, and then it could be 2m, and up to 30m. That equals what? That means altogether there are 300. There are 300 points. 300. But the thing is, even you can use this Gauss function to denote the condition in another way, it does not really help you, because for all these floor functions, we know it has the integral part, it has the decimal part, but it's still, of course, what you can do is you know that m cannot be too small. So all these things add up together. All these m, 2m, 30m should be at least 300. But still, it's not an accurate number, right? So it kind of gets dark. And then the way that makes me suddenly have a hope would be when I notice that. So I notice it's 1/3. This is something you could probably see it immediately, right? 300 points is 1/3 of altogether the number of lattice points. But the next step is when I think 30 squared, then I think about area. And then I think about which part of the square can have an area 1/3 of the total square. Then it is not the diagonal. Diagonal cuts the square in half for the square, though it must be slightly less than the diagonal. It's something like that, right? And then once I have that picture, I somehow kind of like feel comfortable, because I know that once I locate this line, whatever the m must be very close to that. And then I start my real calculation. So here is my calculation. So what is that calculation? That calculation is, so I notice that this is 1/3. So I will focus on a point where here there's a line, and then I do what? I trisect this line, and here is 2/3 of the edge length, and then this area would have be 1/3 of the total area of the square. And what is this point? This point is because it's 2/3 from 1 to 30, so it's kind of like 20, right? And then there will be 10 points on top, and then there will be 20 points on the line below. However, you need to be a little bit careful. In what sense? You need to be a little bit careful in the sense that you see that although this is a 30 by 30 lattice point, then what is the size of this square? The lattice point actually forms a 29 by 29 square. So here we are kind of, when we're talking about the area, this is kind of like a little bit vague, right? We are not really talking about the area of the whole square. Is really not really. This is 1/3. So it's kind of like a big. And for the x-axis and y-axis, actually they are not really in that square. But anyway, let's just do some calculation, because I know that at least it's y equals to 2/3x. So this is a nice equation. And for that nice equation, for that nice m, it would be not that difficult for me to calculate how many lattice points are there. So I will start with x equals 1 to 3, right? So up to 30, right? Then for each of them, as long as I calculate what will be that fraction and how many integers are there, then I'm fine. So if x equals 0, then I get what? Then I get y equals 0, right? So no, I get y equals 2/3. Sorry, we should start with x equals 1. So if x equals 1, y is 2/3. So y has to be at least 1. So there will be 0 points that is below this line, right? Which means actually this is 1, 1, right? So it will be 0. When x equals 2, this is 4/3. So there will be 1 lattice point that's below this line. And when x equals 2, that will be exactly an integer. When x equals 3, that will be the integer which is 2. So there will be 1, 2, there will be 2. And then you go to x equals 4. X equals 4, then that will be 8/3. So it's 2 point something. So there are still 2 lattice points below the line. And then when x equals 5, there will be 10/3, so it will be 3 and 4. So you'll see, of course, the pattern would be every 3 numbers, because they're divided by 3 here, right? So you'll see each group is 0, 1, 2, 2, 3, 4, and then what will be the last? For the last one, x equals 30, y equals 20. So it's 20. And because in each period, these are consecutive integers, so we can write down 18, 19, 20. Okay, so now we have this. Then once we have this, then we need to count how many lattice points are there on the line and below the line. And we need to add up all these numbers, all these 30 numbers together. So what is the quickest way to do? The quickest way to do is you notice that the middle one are all odd numbers, and they are consecutive odd numbers. And we know the sum of the consecutive numbers is perfect square. So 1 plus 3 plus 5 up to plus 19 would be, how many numbers are there? Actually 10 numbers. 10 first. The sum of the first 10 odd numbers is just 10 squared, so it's 100. And what is the total? In each period, the average is middle number. So altogether, there will be 100 times number 3, so 300 points. Okay, very wonderful. Now we find one nice m, and that m is 2/3. Right? So after we find 2/3, then there's another question, and we need to think about it, because they say that there's a little bit of wiggle room, so the m can be changed a little bit, Then my question is, now m equals 2/3 is a good one. So can I increase m or can I decrease m? Which direction? Actually, I can only go in one direction. Could you have a guess for those of you who are watching me? So next step, whether I should increase that or I should decrease that. And why is that? So for this line, there's exactly 300 lattice points on the line and below. And now we want to see what are the other possible choices. And actually, the situation is we cannot really move down. As along this line, we know that we have lots of lattice points. for example, this could be I could see this as first one. Maybe this would be x equals 3, y equals 2, and then x equals 6, y equals 4, and so on, right? So if you move a little bit, then many lattice points, so actually there are 10, would kind of like drop out, would be excluded from the region. So that cannot be good. So the only thing would be you move up. So what you imagine is you can think this line just as a stick, a very, very long stick. You can think all the lattice points, on each lattice point there's a pane. So what you do is you can only move the stick a little bit so that it touches another lattice point. Okay. So what do you mean another lattice point? The lattice point, so intuitively the idea would be the lattice point has to be very kind of close to that line. And now you can do some kind of an analysis. So what would be the analysis would be just draw along each vertical line what would be the lattice point very close to this line y equals 2/3 of x. So when x is has remainder 1 when divided by 3, then for this fractional part would be 2/3. So in order to reach a lattice point, so here you need to have another 1/3. Then this is another 1/3. Then the next one x equals 2, something like that. Then you need to have another 2/3 so that it can reach the lattice point. Right? So the next one actually is exactly on that horizontal line. And so then that means what? That means so which point that really affect us to move too much would be all this point, because this point are kind of closer to this line. So what would be the distance for these points with respect to that line? Actually, the distance are all the same. Why? Because these are all the isosceles triangle you can form. The distance are all the same because this is 1/3. And then what is the difference for them would be, because here what we are doing is we are rotating. It's not we are parallel shift. It's not mx plus b. So we are rotating. So that is why we have to be careful. And when you're rotating, which one would give us the most restriction? It would be the point that is very far away. Because very far away, there's a fixed distance. So what you rotate from the origin. This would make the angle very small, right? So then, and now we are very clear. We need to find among the numbers that has remainder 1 when divided by 3. We want this y to be kind of like as this y can be only slightly greater than the kind of 2/3 of x. So what we should have is 3y minus 2x equals 1. Because for the point on the line, 3y minus 2x equals 0. And then you can see that you choose the last number that has remainder 1 when divided by 3 with 28. 28 times 2, 56. 56 plus 1, 57. 57 divided by 3, you get 19. So this would be kind of like the upper bound of the interval. And then you make a subtraction, and then you get 84, 1/84. And then you check, you see whether you have the answer. Of course, if you don't have the answer, then there must be something wrong. But for the complicated questions like that, because there are so many choices, if you really have the answer, then for me, I would think as long as your calculation accuracy is not really 100%, your calculation accuracy is relatively high, I think you can feel very comfortable that this would be the correct answer. So you see, for these difficult problems, if we want to summarize to see what we can learn, I think the key thing that we summarize would be we need to construct a nice example. So once we have a nice example, then we feel happy. Right? So this is the trick that we should learn from this question. Okay, so the next one is problem 24 in AMC 12B, which is a geometry problem. So this problem is a little bit long, so maybe let's rate it. So ABCD is a parallelogram with area 15. P and Q are the projection of A and C onto one diagonal, and S and R are the projection of the other diagonal with foot S and R. So you see these are kind of have some symmetry there, right? PQ, SR. And then what are the other conditions? They also have some symmetry. PQ is giving, SR is giving, okay. And then what the question is to ask? The question is asking to find kind of like the longer diagonal, essentially the length of the longer diagonal. So how many numerical conditions are there? There's 3 numerical conditions. So the foot between the distance between the 2 pairs of foot and together with the area. So 3 conditions. And for this question, so what would be my next response? My next response is kind of like, I kind of like notice the point symmetry. So if I denote this by O, then what happens? Then of course these 2 diagonals, you see this bit is exactly symmetry with respect to that bit, with respect to O. So in other words, now I want to shrink my focus. In other words, I have a very limited whiteboard. If I can shrink this picture, then my life is much easier. And in a way that we can really shrink because these 2 are exactly the same, right? Okay, then how I shrink? If I only shrink everything into this corner, what we could have. So OP is 3, right? So that is something we have. This is because it's 6 divided by 2. And OS is 4. Okay, so for these 2 conditions, we can exactly restrict it to that small piece. How about the next numerical condition, the first numerical condition, which is the area is 15. You see, the area is 15 is not hard, because if the area is 15, that translates to when you have a parallelogram, the 2 diagonals are bisect each other, so the two diagonals will cut the parallelogram into 4 equal triangles, right? And then for this OAB, then that would have the area 15 over 4. That's it, right? So it's not hard at all. Okay, so now after this analysis, I'm pretty much comfortable because I can focus everything back into this small piece. And so I have a slightly bigger picture here. So what are the small pieces? So I name this is O. So here we have 3, and the OS is 4. Okay, and then what to do? And the area of OAD is 15 over 4, right? These are the 4 conditions we have. And now I will change into a color to do the calculation. So what is the calculation to do, and why I feel comfortable is because I have 2 right triangles. You see, this is a typical structure. I have 2 right triangles, OAP and ODS, and these 2 right triangles share a common acute angle. So these are similar triangles. So similar triangles means what? So similar triangles means all the corresponding sides have the same ratio. So what I'm going to do is this is OP is 3, so I'm going to assume that PA is 3 times A. Why? Because I want the OA to have a nice label. So what would be, for example, what would be the OA? OA then would be everything have a factor 3, then it is 3 times A squared plus 1 by Pythagoras Theorem, right? All right. And now in order to find the equation, what we need to do is we need to use the area, of course. Then how to denote the area? The area is 15 over 4, right? The area is 15 over 4. That equals what? That equals half times the base times the height. The height is already clear. It's 3A. So what would be the base? The base is OD. You'll see that everything is, the ratio is 3 to 4, right? Because it's 3 here and 4 here. So given that OA is 3 times square root of A squared plus 1, then the OD should be 4 times the square root of A squared plus 1, right? And now we do a little bit of simplification. And this 3 cancels out with this 3, and then the other side becomes 5. And also we can do a multiply. We can move the other all the constants to the other side. So what we are going to get would be 5 over 8 equals square root A squared plus 1 times A, right? And now we need to solve this equation once we get A. And I think pretty much we get everything, right? Because we'll get DO by that. All right, so how to get A? How to get A would be take a square. Why we take a square? First, there's a square root. So that guides you to take a square. Second, once you take a square, you get A squared plus 1 times A squared. And then you can change into another variable. So you can just assume A squared as X. If you assume that A squared is X, and then you will get just a not really nice, but at least you get a quadratic equation, right? X plus 1 times X. So that would be X squared plus X. And then there's a constant term, and that constant term span out would be 25 over 64. That equals 0. So once I have the quadratic equation, the first thing I thought would be, can we do a factorization? But then I look at 25, I pretty much give up. Right? So for 25, there's not too much you can do. And it can be only 1 times 25. And you want to get the kind of the root difference, the two number difference is 1. So it's hard. So then what to do? We just directly plug in the quadratic equation formula, negative b plus minus b squared minus 4ac, and so on, right? So what are the 2 roots? The 2 roots, we directly write down x would be something over 2 negative b negative 1 plus minus, what's inside the square root? B squared is 1, minus 4ac becomes plus 4ac because there's a negative sign, 25 over 64, right? And then now let's do the simplification. And so the first part, there's nothing to simplify. And maybe we just write down here. So let's simplify this first. So this would be, you have a 64. So 64, you're taking the square, it will be something over 8. And then what's the numerator? The numerator 4 times 25 is, probably better would be you cancel out this 4 with 64. You get 16, right? So 16, you get 4 out. And then the 16 plus 25 is 41. So it's actually would be plus minus 41. And then the denominator becomes divide 4, divide 2, divide 8. And then here would be 4, right? Negative. Right. Okay, so you get x. So now we come back to the original, what the question is asking us. The question is asking us to find, not BD, but the length of d squared. So BD squared, okay, remember, what we need to find is BD squared. BD squared is what? BD squared is 4DO squared, right? So BD squared is 4DO squared. And then what is 4DO squared? DO, we already said that DO is 4 times square root of a squared plus 1. So what we do is we take the square again. So that becomes 64 times a squared plus 1. And now I feel happy because when you plus 1, you only plus 1 here. Then you just remove this plus sign, the negative sign into positive sign. Then that becomes, and also because it's 64 divided by 8, so you get what is 8 times 4 plus square root of 41, right? And then you get you do the calculation, you get the M and P, and you're finished, right? So for this question, the thing or the trick, I would say that will be the structure analysis in the geometry problem. So when you deal with a geometry problem, this question in the nice that it's already giving you a picture. And if you don't have picture, the one thing you can always to think about is, how do you how you draw the picture step by step. And that kind of structure construction also give you some hint, like how the condition restrict the structure, and that kind of restriction could lead to an equation, and then you can find out all the lengths. So that is the trick I want to see. All right, and next is a complex number problem. And for that complex number problem, and it's problem 18. And when I first did this problem set AMC 10B, actually I skipped that problem at the beginning. Because of what? Because this equation is so complicated. So all these are so here when they say the absolute value, so that means, let's review, that means the definition for a complex number, because it's the real part is an imaginary part, and then what will be the norm of z? So that will be the square root of the real part square plus the imaginary part square, and then take a square root. So that would be the definition of the norm of z. Of course, here a, b are real numbers. The thing is, this is too complicated, right? It's all the things about norms, and then they have the square, they have the other square, and this 31 is not a nice number. And but amazingly, and they ask you to calculate something which is quite concrete. So I have no idea at the beginning, then I skip. And then after I finish all the other questions, when I come back, I suddenly realize something without any calculation. What do I realize? I realize that even, I use brutal first. I just plug in z by a plus bi and then expand out all the norms. Unless there's a nice thing that there's no square root, because we have the square everywhere. Then this would be what? This would be an equation about a and b. And the key thing is, this is a unique equation, the only equation that about a and b. As it's different than you have equation about complex numbers. So when you have equation about a complex number, so essentially you have two equations. The real part are the same, the imaginary part are the same, then you can get a system of equations. But here, because everything is about the norms, so it's our real numbers. So you'll see that this means that we definitely have two unknown, real part and the imaginary part of a complex number, but we only have one equation. And then what would be the possibility? If you have one equation and you want to solve two variables, this equation must be very special. It could take something like that, which is what? Well, I draw a bunch of zeros. These are not really zeros. These means some square plus some square plus some square equals 0. This is really a 0, right? If you can express as this way, then my each fat egg would be actually has to be 0, right? Because if you get the squares, then there's no other choices. Then immediately you get many equations. This is 0, this is 0, that is 0, something like that. So then after this kind of analysis between 1 and 2, I know my way to do it. I will just plug in a plus bi and do the calculation, and my objective is to completing a square. So how to completing a square? Is it possible to completing a square? And so expand out. For example, why we have this complicated thing? Because it's a square plus b square, and then here z square plus y is what? Is a plus bi times a plus bi plus y, right? And a plus b, the real part is a square. I square is negative a square minus b square, and then plus 1. And for the imaginary part, it's ab, so 2ab squared, so we get that. So we'll continue to do the simplification. And you will get there's a degree 4 term, which is a to the 4th plus b to the 4th. And the a square b square term, there's a negative 2 here and there's plus 4 here, so we have 2a square b square. When for a square, we have 12 here, we have 4 here, so we have negative 8. For b, we only move that to there. And also we have a term because of the crossing term in a plus 2 square, and we have a 40. And then how to form the completing square? So for here, a to the fourth plus b to the fourth plus 2a squared b squared, that's already tell you the method. The method would be just a squared plus b squared. Right? And then we need to find the constant. So how to find this constant 6? Actually, this constant 6 coming out of this negative 12b squared. Why? Because there's no other b terms. So, we have to digest this negative 12b squared into that perfect square. And then the only way to do it is to form a crossing term. So if we negative 2b, so it's 2 times b squared times that constant. So the constant has to be negative 6. Of course, that also leaves another term which is negative 12a squared. But no worries, here they have 12a squared, then we plus 4a squared, and then plus 4a. And then constant term is 40 minus 36 is exactly 4. Yes, we get another perfect square. Okay, so once we have this perfect square, then what we have? Then we know that a plus 1, then we do have a system of equations about a and b. So a squared plus b squared must be 6, or the norm is square root of 6. And a plus 1 is 0. Of course, you get a equals negative 1, and b is plus minus square root of 5. And then you can do the calculations. Right. But the idea is once you know that you need to complete in a square, that's it. And of course, then I check the official solution. The official solution says this, but it's very similar there. But it's only kind of like organized in a slightly simpler way. And because they express everything in terms of z and the conjugates of z by using that formula. That formula, in many other cases, would be very useful, which is z times its conjugate is a z norm squared. But for this particular question, I don't myself do not really like that method, as this somehow make me feel difficult to see the squares. For me, I feel very comfortable if I just write down the real and imaginary part explicitly. But of course, these two ways of forming the completing square are essentially the same. Okay, so completing squares. That's very important, given that we have to deal with so many quadratic things in the computation. Right? All right. So now we move on to the next question. So the next question is back to problem 23, and also in AMC 10B. So that question talks about 3 balls, and the difficult part, the complicated part is about a ball is thrown into bins, but not finite number of bins, but kind of infinite number of bins. So the bins are numbered with all the possible positive integers. And given that there are infinitely many ways to throw out each ball, but all the probability has to be summed up to 1. So that's why we have this probability measure. So the probability to throw into the first bin is half. Into the second bin is 1 divided by 2 squared is 1 over 4, plus 1 over 8, plus 1 over 16, plus so on, right? So this is exactly a geometric sequence, and the first term is half, and the ratio, the common ratio is half, so half divided by 1 minus half, so you get this half times 2. So yes, so the probability, yes, to add up is 1, right? And of course, this should be the case, otherwise this problem must be wrong. Okay, so the probability that the balls end up evenly spaced in distinct bins. So when you read the AMC 10 questions, you also need to be careful about all the conditions. For example, the conditions about distinct. They say that they have to be in different balls. That's really a condition. It's only, expressed by a word. and evenly spaced. So evenly spaced, it means what? It means you throw the 3 balls into the three banes, you get 3 numbers, and that 3 number actually form the arithmetic sequence. And we do not care about the order, so that is why we have this kind of example. So it's first you have 3 plus 7 is 10, and then 10 plus 7 is 17. So it forms an arithmetic sequence, and that is why we can arrange it, right? It does not mean the first ball has to be thrown into a bin with smaller number, and the second ball is middle number, and the third ball is large number. Okay. So we have this kind of like ideas, and then what to do? What to calculate? What to calculate? Normally, when we calculate a probability problem or a counting problem, we know what. So in the counting problem, we have the principle, addition principle and multiplication principle, which means all these principles actually just give us some ways to divide the problems into several mini problems, and so that it's easy for us to calculate. And then for this question, actually, if you form this kind of philosophy, you will find it's not that difficult. Okay, so then what are the steps? What are my steps? My first step to do is I will think that the 3 balls have no order. When we talk about the 3 numbers, we always have to list these 3 numbers from the list to the largest, right? So in that way, once we fix that 3 numbers, the 3 big numbers, how to assign the balls, actually we could have a permutation. So that is why I have the first step. My step 1 is, so the balls related to the numbers, there could be a 3 factorial permutations, and that factor is something that I have to multiply in the last. And then we need to consider, I want to consider what would be, so I can name the 3 balls would be just the smallest, the middle one, and largest one. And then I see what are the 3 numbers that can form the arithmetic sequence, which means evenly spaced. The simplest one would be what? The simplest one would be 1, 2, 3, right? Definitely this is evenly spaced. Then what would be the probability? For 1, it would be 1 over 2 to the power 1, then 1 over 2 to the power of 2, and 1 over 2 to the power of 3. Then you get 1 over 2 to the power of 6. Okay, so this is a simple calculation. We'll use multiplication principle. Then what would be the next? The next would be 2, 3, 4. Why I see here 1, 2, 3 is the next. So the next step, that means the next step we consider what? We consider what could be the common difference D, right? So D could be 1, could be 2, could be 3, and so on. Now what I'm considering is the first simple case, which is D equals 1. So for D equals 1, it's 1, 2, 3, we get 1 to 2 to the power of 6. And then now let's continue. Continue to what? 2, 3, 4, right, would be the next one. Then what we probably would be this. And if you can observe these 2 numbers, what do you find? You'll find the denominator becomes slightly larger, giving that the base number has increased by 1 for each of the 3 bases. So here there will be 1 more 2 here, 1 more 2 here, 1 more 2 here. So altogether, the number of factors 2 on the denominator increased by 3. So you know that this would be the first number times 1 over 8. And then you could see, imagine the next one. What would be the next one? The next one would be 3, 4, 5, right? So it will begin to increase by 2 to the power of 3 on the denominator. Okay, now you suddenly notice, okay, then for the case that when the evenly spaced 3 numbers are with common difference 1, then we can list all the possible probabilities. Of course, it's an infinite sequence, right? And what will be the sum? The sum is just that, right? The first term divided by 1 minus the common ratio. Okay, so that deals with D equals 1. And then you move on to the case where D equals 2. And you'll see whether it's in a similar format. And nicely, it's in a similar format. When D equals 2, there will be 1, 3, 5. So 1 to 2 to the power of 1 plus 3 plus 5 is 9. And then next is 2, 4, 6. You know, each time it's like you add 1 to each term. So you always get a common ratio, which is 1 over 8. Okay, so So for this, you can write it down. Then for this sum, for d equals 2, you can write down the other factor to be 1 over 2 to the 9, and then still 1 over 1 minus 8. Okay. 1 minus 1 over 8. And so that related to d equals 2. Okay. So now let's think about like what would be the relationship between these two. So this is d equals 1, this is d equals 2. And if you have a comparison, you will find all these sums forms another kind of like common ratio sequence with common ratio 1 over 8. So there's another geometric sequence, and this geometric sequence becomes smaller and smaller. So you can use that infinite sum formula again to use 1 divided by 1 minus the common ratio. Okay, then these three parts multiply together. So here in this step 2, it's kind of like we consider not only one infinitely many sequence, but infinitely many kind of like in lattice, in matrix. So two-dimensional geometric sequence add up together, and then you will get that. You do a simple cancellation, you will get the final answer is 6 over 49. And so the answer is A. So that is that one. So for that one, I think as long as you can cut it into very concrete steps, and in the end, it's reduced to, the three numbers, and then you list out the probability. You find a nice way, an organized way to do the addition. Then it is not that hard. All right. And now we can move on to the other shared problem in AMC 10B and 12B, which is a game problem. So this game problem, for game problem, especially for this type of problem, it's really hard to explain by words. So that's why they kind of like give you examples. When I first see it, I feel confused as well. I need to look at the examples, then I have better ideas. Because here the word they define as something kind of like called a war, and then also there's several wars of breaks. So it's quite confusing. So actually it means what? It means for war, it just means several pieces. There could be gap. So each war would have several pieces, and each piece is actually several consecutive breaks. Right? So that is the definition of the war. And what is the action? What is the action allowed in each step? The action would be removing one break or two adjacent ones. So 1 or 2 adjacent ones. So 1 and 2 must be some key numbers. And to understand the process, we can look at this example. So here there are 4 breaks. If I remove the leftmost one, what we get? Yeah, we get 3, 2. So how to achieve this? Well, to achieve this actually means we remove this one. You remove this one, then you kind of like cut this first piece into two separate pieces. And also that's why they have 2, 1, and then the remaining 2. And what about that? That means we just get these two adjacent pieces together. So actually there's one piece less. Okay, so these are the process. And then the question asks, under what condition the second player would have a guaranteed winning strategy? So when we deal with this kind of game theory, hopefully you already deal with some easy game theory problem. So for me, this type of the problem, this would be something like that. You have a bunch of marbles, and there are 2 players. At each time, every player maybe can only pick 1 or 2 marbles, and then who can get the last marble wins. Who has the winning strategy, and then the idea is we form pairs of 3, because if one person pick up 1, the other person can pick up 2. If one person pick up 2, the other person can pick up 1. So by one round, you can form a pair of 3, right? So if originally the total number of marbles is divisible by 3, then the second winner always has a winning strategy, because no matter whatever the first player picks, he always make the other the kind of like the other possible cases to make a 3, and then in the end, after each time he finishes, the number of marbles left must be a multiple 3. So the first player cannot pick up all of them, because each time they can only pick 1, 2. So forming the pairs essentially is the essential trick in kind of the game theory. So how to form the pairs? So here, of course, there are difficult things, right? Because in each one there are more than 1 pieces. Actually, in the question there are more than 3 pieces. And in order to form pairs, maybe we better to have something which are the same. So that's why originally what I'm thinking is I think 6 to 2. So why I think 6 to 2? Because I see, okay, this is already a pair, and maybe, right, this is already a pair before the first player starts. So maybe if the first player pick anything in these 2, then the second player best can do the same for the other 2. And then any player do anything on the 6, then the best, because the 6 is very big, very long, right? If the first player do it on the left, the best can do it on the right. So it's kind of like, I noticed there could be one situation that caused the trouble, which is if the first player start with that six piece, and what he does is something like that. 2, 2, 2. So it means that he just take away the middle 2 pieces, then what's left? Then this wall would be breaking into 2 pieces, 2 and 2. So after this first player, so this is after the first player A, then you have 2 pairs. Then A has a winning strategy. And then similarly, maybe you'll see, okay, so there's no way for that. Because 1, 1, he can do the same. Also, it's 2, 2, 1, 1. So he can form 2 pairs. And similarly, because 3 plus 1 is 4, so he could have take 2 pieces to make this 6 become 3 and 1. So make this 6 become 3 and 2. And then after A take the first action, they already make the wall in pairs. So the B cannot have any winning strategy. So in this sense, we know that all these 4 choices must be wrong. So the only correct choice has to be 6, 1, 2. And of course, there's a way to prove that 6, 1, 2 is right, because you can list all the possibilities. So here I list some. So if A just take 1 or 2 pieces from this longest wall 6, you get something like that. Then what you do, for B, he can always try to construct to form a symmetry. For example, for after A get this, you have a 5, you have 1, 2, then you can break this 5 into 1, remove the 2, and then have 2, and then what's left would be 1, 2, 1, 2, so there are 2 pairs. And similarly, you can list all the other possibilities, and you could see that after 1 round, the best can form pairs, and then that he has a winning strategy. So this is the game theory problem. And for this game theory, we need to think about would be use symmetry and use pairs. All right. Now, let's move on back to 10B, and that is a geometric probability question. And for this geometric probability question, it looks like what? It essentially actually to calculate the areas. And we know that for the geometric probability, how to calculate the probability would be on the numerator, it is the nice area, the area of the nice region, and on the denominator, it's the area of kind of like the total region. Okay. So now the question says that we have a square with length 8, and each corner here the length is 2, and in the middle one, and it is a diamond. Of course, diamond is also a square, and with length 2 square root of 2. So how to see this picture? So for me, the first thing I see is, in my mind, I have something like that. This horizontal line, this horizontal line, this horizontal line. Why I have this? And because I cut this 8 by 8 square into a bunch of 2 by 2, a bunch of 2 by 2 squares. You know that now the computation is online. Well, remember that we are allowed to use the graph paper. So the most efficient way to do the computation is you first prepare enough blank graph paper before the computation, and then in the computation to draw this picture. It will be very nice. You just find in your graph paper a 4 by 4 grade, and you can draw that, and then you can start to do the calculation. Or you can draw 8 by 8 grade if you want in your graph paper. And now we analyze what could be the area of the coin. For the coin, we see that one thing that I said in the last explanation about 10A12 is, once you have a disc or you have a circle, there's one thing you always need to consider would be the center and possibly the radius. Okay, so now in order to determine where the position of the coin, so essentially what we need to determine is the position of its center, right? So we see where is its center, right? So of course the center has to be within the square. And within the square, what shall we do? And it cannot be very close to the boundary, as they say that it's trapped. You see, a circular coin is completely contained within the square, right? There cannot be any part out of the square. So the center needs to have a distance of at least a half, which each of the sides, because the radius is half, so that the coins has to be completely inside the 8 by 8 square. And so each boundary is half. Okay, so given that each boundary is half, so what would be the size of this right square? This would be 7 times 7, which is 49. So when I see this 49 and I look at 196, I smiled. Why? Because 49 times 4 is 196, right? 49 times 4 is 196. Then that means what? That means our denominator should be right? Okay. So now let's carefully analyze what would be the whole region, right? So what would be the whole region? The whole region would be, we need to see that what are the possible area. Of course, there will be 4 cornered ones, and then there's a centered one. So maybe let's look at the centered one first. The centered one, they see why I want to use the grid. So with the grid, you know what? You know that this black region definitely would be the good region for the center. And so the area would be just 2 square root of 2 squared, which is 8, right? And then it could be not exact, the center could be outside the black square, but has distance less than or equal to half with all these 4 sets. Then what you have? You would have, this is half, and this is square root of 2. So what would be the area? The total area for these 4 little rectangles will be 2 square root of 2 times half times 4. So you get 4 square root of 2. Okay. So now you have 2 pieces. And then the 4 corners. The 4 corners would be the 4 corners, if they put together, they will form a circle. And that circle, of course, has a radius r equals half. So then that becomes half square times pi, right? Half square times pi, so it will be 4 over pi. So that would be pi over 4. And now once I see this 4, I feel very happy, because that is where the 169 comes from, 49 times 4. So here for my beginning situation, and there's one last part I need to calculate, which is the corner. How big is the corner? Of course, it has to be slightly bigger than this black triangle, isosceles right triangle, which is inside this 7 by 7 square. And how to make it inside? So again, that this point has to have half the distance half with respect to the boundary. And here the tricky part thing is, then this big isosceles triangle, you need to be careful, and this length is not 1 plus half, it's not that, but you see this has to be slightly bigger than half, because this is kind of like the hypotenuse of isosceles right triangle with the arc length half. So what we should write this should be actually 1 plus square root of 2 over 2. So this one. And then you take a square, and then you get 1 plus half plus square root of 2. And then you combine the integers and square root of 2 part, you get 16, right? 17. And then because we need to over 196, so there's a factor 4. So that's why we have 17 times 4. So we get 68. Right? So you'll see here, I do not write down all the list. So I directly use 4 times 4 mount after I know that here there's not divided by 4. So all these ways can help me to calculation, to write down less word and to calculate a little bit quicker. Because in AMC, it's really every second counts. And use grids can help us to get a better structure of the problem. All right. So next one is a probability problem again. So that's why we know that normally in the AMC computations, all the probably half of the hard problems are probability and counting problems. Okay. So in this problem, they say that there are 3 people, right? The 3 people are A, B, C, and they put 5 colored boxes. And the key condition is at least 1 box receives 3 blocks of the same color. Okay. So here we know that there's just 3 people that have the randomness. And it's kind of like this is an analogy would be 3-dimensional solid geometry versus 2-dimensional plane geometry. So 3-dimensional things is always difficult because it's hard to draw the picture. And here there are 3 people that randomly through the block scheme. That's too complicated. If each scenario, you have to draw a cube to denote it. But if you only have 2 people, so in the AMC 8 question, probably you already did many things like that. So if you have 2 people, they throw a dice or something, these are all the possibilities, and then you can list all of them, right? And then you form a nice table, and then you do the count, right? But here we have 3-dimensional, but after you think a little bit about it, because you see that all the 3 blocks have the same color. So what we can do is we can fix the color for A. Or in other words, we probably can do that. We can color the box by A's block. So if A throw a box into red, then you just color this box as red. And then the question becomes what? You have 5 boxes, 5 colors. And the B and C are through the balls into these 5 boxes. And the probability you calculate is to what is the probability that for at least 1 box have the 2 blocks with the same color, right? With that box. And then you can list numerical situations. You can list like that. But then still it's not easy. And so what to deal with it? So after I find out that the hard part actually becomes, so I show you my scratch paper. Hopefully you can, this remind you something. So the situation is at least one box. So this is the part that makes the situation hard, or in a sense that gives you the hint. So this box could be the first box, could be the second box, and so on. So here I write down the box, I label the box instead of colored for easy writing. And then there will be some situations like that. So we know that then what means it will be means there are 5 circles, right? To denote the 5 situations, but it's only one of them, right? So when you have these kind of like repeated things, then what would be the thing that appear in your mind? That should be PIE, principle of inclusion and exclusion. And we know that maybe I write down the 3 set cases again. That would be what? So in order to calculate the union of the elements in the 3 sets, which essentially corresponding to the condition at least something, then you add up all the number of elements in each set, and then you overcount it, right? So there could be some elements that are in both sides. Then you need to minus all the intersections. And but then you deduct too much. You need to add back actually all the number of elements in all the 3 sets. So here the situation appears would be alternating plus and minus. So here is plus, and here is minus, and then it's plus again. Plus, minus, plus, and so on. Okay. So that is a principle of inclusion and exclusion, and for us, then it can be applied to here. So there's one box, which box, either number 1, 2, 3, or 5. So there are 5 choices. So that you'll see that for that box, you must receive the two colored bricks with the same number, right? So what will be the chance? That will be 1 over 5 squared. Okay, so now if you see that you want to fix 2 boxes, so how many ways to select the 2 boxes would be 5 choose 2. And then for each case, for each B and C, what is the probability that he has threw the ball number 1, 2 into the box 1, 2. So for the first one, the probability would be 1 over 5, and then for the second one, there are 4 balls left. The probability would be 1 over 4. So that's why we have this square. And similarly, if you fix the balls in 3 boxes, that would be 3 and 4 and 5. So even it looks like complicated, but as long as if you have a clearly understanding statement about the principle of inclusion and exclusion principle, and you should be able to write down this in 1 minute. And then the next challenge would be how you do the calculation. The calculation is too complicated, and especially the denominator is too big, and we know that to do the addition and subtraction, we need to find a common denominator. Now here, how do I find the common denominator? The thing I notice is that I notice this. I notice these 2 fractions are the same because here is multiply 1, right? So how to get the common denominator? I didn't get 2 copies of 5 factorial. I noticed that this was the same, so it's minus 5 plus 1. So altogether minus 4. So I can cancel out a 4 here. Then I get 5, 4, 3, 2, and 5, 3, 2. So that is my denominator. The denominator then incorporate these 2 terms, and then there will be minus 1. Okay. So now my next task will be find the 3 numbers for the first 3 terms. This term is relatively easy because it is essentially 1 over 5. So this is 120 times 30 is 3600. So 1/5 of it that will be 320. So how to deal with this fraction? This fraction, you'll see that they has 5 times 4, which is here. They also have a 5 times 4, which is here. So here we have an additional 9, and then on top is 10, so that's why it's 90. Similarly, you can get this is 10. Okay, so you'll see this is the mistake I made at the beginning. So I forgot to minus 1 plus 1, then I get 1641, then I got stuck. So 1641, I don't know what are the prime factors. Then what I do? So I come back. Okay, I notice that there's a minus 1. So this will be 639. And when I see 639, I feel happy because it's divisible by 9. So you can cancel out 9 both on top and the bottom. I get 71 plus 100. So 471 would be the correct answer, and 475 is there. So I feel quite happy, and move on to the next question. So for this one, you see sometimes that is why that you need for AMC in order to achieve the high score. It's very important that you have a clear mind and you can take action decisively. So for this question, actually it turns out there's no other better method. So if do not get stuck, just like see you list this and then you say, oh, that's too complicated. Let's try to find the answer. No, this is you list out this and that. There are not so many terms that you should be able to have the numerical. You have to should be able to have the capacity to do that numerical calculation. That is a capacity that you need to build up if you really want to achieve a very excellent score in AMC. All right, so now we switch into a geometry problem. And that geometry problem is, so it has a very low correction rate, but I want to show you that this geometry problem is so simple and everything is natural. So it's about how many points are there. So let me check if everyone's still there. So if you know how many points are there, can you type me that number to me in the chat? So how many points are there in the graph? Anyone? So this is a nice graph, and so there are many segments with identical lengths, and altogether, actually, there are 7 points. So here we have 2 points here, and this is currently kind of like symmetry. When we do structure analysis, how we do structure analysis. So for this question, how I draw it, or how I construct it. If I have actually, I have this kind of like some what is called some rubber thing. Maybe I use some rubber to denote these 7 points, and then you have sticks. So I glue these 7 sticks around these 7 points. So what shall I do? It would be I first form kind of this diamond, right? So this diamond actually constructed out of 2 equilateral triangles. I first construct this diamond, and then I have 2 kind of diamond. So it looks like the 2 wings of a butterfly, and then I make them kind of like close to each other to control the CD, to make the CD is exactly the same edge length. Then I would be fine. Okay, so this is how the picture is constructed. But once you know how the picture is constructed, I think immediately you should be able to know how the areas to be calculated. Because here we have an isosceles triangle, so a natural thing to do is we should be drawing its medium, or the line perpendicular to its edge, right? So that is the thing that we should naturally do. And once we do that, we should also remember all the, and then also because of symmetry, there's another height, or the medium of the base that we could draw. And then we can do the calculation. So remember that in the equilateral triangle, what would be the height? Square root of 3 times, square root 3 over 2 times of the set length. So that would be the square root of 3. So that would be square root of 3. So here is 1. And then in this isosceles triangle, you will get, that would be 2 square root of 3 square minus 1 square. So that would be square root of 11. So this height is actually square root of 11. And then how to calculate the area? To calculate the area is you consider the middle isosceles triangle. The middle isosceles triangle has the area half times the base 2 times the height square root of 11 plus what? Plus these kind of obtuse isosceles areas of obtuse isosceles triangle. There's another obtuse, and these 2 that are outside of the center isosceles triangle actually forms 2 equilateral triangles. And for equilateral triangle, we know the area is square root of 3 times 4a squared the side length square 2, and then what you get. So these two cancel out, so you get square root of 11 plus square 2 times square root of 2 squared times 3, so you get square root of 12. Okay, so there you know 11 plus 12, so 23 is the correct answer. All right, so that's problem 10B. I don't really need that many space. So you'll see for this question, we see the equilateral triangle, we see the isosceles triangle. If you draw the key auxiliary lines, which in this particular two shapes are the mediums, then it becomes a piece of trick. Okay, so this question also has very low correction ratio, although I think it's not that complicated. So what they say is, they say that they have an isosceles trapezoid having parallel bases A, B, and C, D, and so therefore area. So the trick is to calculate what? To calculate the ratio of AB over CD. All right. So now you observe this question, you see what? So we need to find the ratio, right? And so we need to set up some equations. So you see how this point. So this time, what kind of structure analysis you do? So the structure analysis you do is you could find out that. So this point cuts this trapezoid into 4 triangles. To me, among these 4 triangles, I like 2, I hate the other 2. Which 2 I like? I like this one that associates with CD, and I also like the one that associates with AB. Why is that? Because for these 2 triangles, I can draw the height. I can draw the height, and also, not only I can draw the height, but also these 2 heights are related to the height of the whole trapezoid. In other words, you can imagine how you determine or how you locate this point. What you do is, you at the beginning, this one is very small, right? And then so you can scroll down a little bit to gradually will satisfy this condition 2. And this condition 2 is what? This condition 2 is actually altogether 2, 3, 4, 5, add up together, that's 14. So it's kind of like 1/7 of the whole area. And then to construct 4, you get kind of increase, and happily they meet each other. And I do not really care this 3 and 5 because it's very hard to calculate the area. And also, I kind of like notice one thing. If I kind of like move this point along that parallel line, what would happen? So I can keep this 2 and 4. So I keep this 2 would be, of course, have the same area. Why? Because it's the remaining area of the trapezoid, but it does not change this 2 and 4. So it's kind of like I can move this point along these lines, and along these lines, then it will not affect this 2 and 4, but 3 and 5 may change. In other words, I should think 3 and 5 as a unit. And then that thing would make us have a better life. So what do I mean? I count 3 and 5 as a unit. So here is my plan. So my plan is, given that in order to calculate the area of trapezoid, there are 3 key things: A, B, right, and then H. And I name this as KH, and I name this would be 1 minus KH, right? Because altogether it has 3H. So K is kind of like ratio. And then I can start to write down my equations. So how many unknowns are there? It's kind of like 4 unknowns, right? So what is my equation? So I will have this half times A plus B times H. That is what? That's the total area of the trapezoid. 2 plus 3 plus 4 plus 5. So that is 14. And then what's next? Then what's next would be, I have half A times KH equals 2, right? I have half b times 1 minus kh equals 4, right? Okay, so somehow I like this because, in a sense, you see these three equations as all the three equations kind of like a similar format. It has h in it, and it is half, and also there's no fraction. And then I can try to use this to mingle and try to form my equation. So what is the equation to form? And so what we can do is we can then have something like that, right? So you see what is AH? So AH then would be 4 over K, right? And then what is BH? BH would be 8 over 1 minus K, right? And then what is AH plus BH? AH plus BH is 28, right? So immediately we will get the equation 4 over K plus 8 over 1 over K. That equals 28. And so there's a common factor 4. Of course, you can cancel out. Then what you get is 1 over K plus 2 over 1 minus K. That equals 7. Right? So we get something like that. And then you'll see this is the equation about K. So the nice thing would be, once we have the equation about K, then we can get it, right? We can get K. Then what is the question is asking? The question is asking AB over CD, which is B over A. So how to form B over A? You take a ratio here, then it can be expressed in terms of K, right? So B over this over that, you get B over A, and all the other things in terms of K. So you know that what that step is finished, right? So then you can get K, and then you can get B over A. As the time is limited, so I will skip the steps. But the way I do it is I want to show you that after you have this, then it's already a very nice, elegant equations. Then the calculation would be not that difficult. All right, so this question, but unfortunately also have a correction ratio less than 10%. So try to design an equation in a nice way to start with, and so that you could have a better life later on. And this question is kind of like fall into the similar idea, how to form a nice equation. Okay, so now let me first read the question, draw a picture. So ABCD is a rectangle, it's in a plane. And then what we have is we have a point M outside of this plane ABCD, and then we can construct a pyramid, and that pyramid is DABCD. And given that we have the right triangle everywhere, then we can use Pythagoras Theorem, and of course MA, MB, and MC would be greater than MD, right? And they say that MA, MB, MC are consecutive odd positive integers, and also in that order. So how to set up the variables? To set up the variables, I think that's natural. So how many free things to choose here in this three-dimensional thing? So to determine a rectangle, we need two things, the width and the length, and to determine the height, we need another thing. So the way to do it is to set the variable naturally. We should set this as h, and then one is a, the other is b, and we may assume that a is less than b. Then what it states that it would be these three lengths, because it's a length. So by using the Pythagoras theorem, so we need to have a square root, right? So these three are the three consecutive odd integers. And of course, you see, you can see, oh, then that means what? That means the difference is 2. Okay, so you can form this minus 2, and you try to solve it. But that's still too complicated. I do not like the idea of what? The square root. So what I'm going to do? So what I'm going to do is I'm going to write down in the other way. Try to avoid the square root. So how we can avoid the square root? And maybe you keep this picture in mind, and let me see that this is a way that to help you. So when I solve this question, actually I don't draw this picture. I just imagine this picture in mind and directly have this. Okay, so now I'm going to move on to the next page to have more spaces, but hopefully you'll still have my picture in mind. And what would be my equations? My equations is I would assume that these two are the integers. Write it down explicitly so that I can avoid the square root. So x squared plus a squared equals 2n minus 1 squared, x squared plus b squared. That would be the next. That would be 2n plus 1 squared, then x squared plus a squared plus b squared. That would be 2n plus 3 squared, right? Okay, so now you'll see I have three equations. I introduced other variables, but then the nice thing is I don't have any square root. So once you have these squares, then it really helps you to get things better. Why? Because immediately you'll see what? A squared. What is a squared? A squared would be the difference of these two. You take a difference, you get a squared is what? It's 2n plus 3 squared minus 2n plus 1 squared. So here you feel happy, say, oh, I can express a squared in terms of n. So I expand this out, not do that. So what the best way to do is you use the difference of the squares formula. So you add up these two terms, you get 4n plus 4. And then what is the difference? The difference is 2. So that is 8n plus 8. Right? Okay, so this is 8n plus 8. Now what you see the condition, then you see the condition is, okay, so this is a perfect square, and we know h is the integer, right? The only integer length is h, right? So here, this integer length must have some restriction. So now I can express h in terms of n, so that would be nice, right? So what is h squared? So h squared is 2n minus 1 squared minus a squared, which is minus 8n plus 8. And you do a little bit expansion, what you get? You get 4n squared. So this is 4 and this is minus 12n. And then minus plus 1 minus 8 minus 7, right? So what we can get is this would be 2n minus 3 squared minus what? So 3 squared is plus 9, so minus 16. Okay. So what is 16? 16 is actually 4 squared. Do not forget 16 is 4 squared. So here comes the part. Of course, one way you can do is you can now use the difference of squares to do that. But if you build up enough problem knowledge, how you can do it quick? Okay, square, square, square. What do you think? You think about Pythagoras triplets, right? So it must be, there's 1 4 square, it must be 3 4 5. So h has to be 3, and this has to be 5, so which means n has to be 4, so 4 square 5 square minus 16 equals 3 square. Okay, and then we can plug in, right? So h is 3, then what would be a? So a would be n is 4, so n would be a would be 40. So the volume would be 1/3 times this h cancel out, and then the other one would be 40. So how about b? So B you can just calculate. So you plug in n equals 4, you get 9 squared is 81. 81 minus 9, you get 72, right? And now you do a little bit of move out all the common square parts. So here you can move out 9, and then you have 8 left, and then you can move out 4. You can have 16. So that would be so actually what you can move out an 8. So here's an 8, here's an 8, right? You can move out 8, you can move out 9, and then there will be 8 times 3 times square root of 5, right? So you know that A is the correct answer. So for this question, it's just to use Pythagoras theorem for sure. But of course, again, to write things in a nice way, so you only need to deal with the integers and the polynomials, but not any square root. All right. I think that's finished the 10 most difficult problems by Hong Kong and Macau participants. And so what would be next? So both both A and B version of AMC 10-12 finished. So the next part would be for each computation. So there are 4 computations. For each computation, there will be a cutoff scores determined by MAA. Then for the AMA, so you can attend the AMA on March. So I expect the cutoff scores to be released around late February. And given the time difference for the AMA 1 and AMA 2, the date will be 1 day late than the official computation date in US, which is on Thursday, March 11th, as well as Friday, March 19th. And good luck, and hopefully you could see the invitation email very soon. And for now, this session finishes, and we will keep you updated about the AMC information by email. And if you want, you can also join our public account in WeChat as well as in YouTube. All right, so that's it. See you later. Bye bye.